calculus students, Dr. Schragi here, and we are moving forward with our class. We are now in section 4.3, I believe, in your textbook. It's called maxima and minima. And what we're doing is we're working with graphs of functions, like the graph of the function that I have right here. And what we're going to be doing is finding ways to describe things like these points that are they're definitely the very biggest in this function, or like this point, which is the biggest around it. I mean, it's downhill from both sides there. Or this point, which isn't the smallest value in the function, but is the smallest around it. And that's what this whole business of maxima and minima is. Make sure that you get a copy of the handout that I have. It's called Maxima and Minima Handout, and it's a little bit big. I think it's 7 pages today. But a lot of it is just like Desmos graphs and so on. So there's going to be reasons why we want to find these functions. We want to find like the maxima and minima, and they're often important, like in a story problem. Like maybe this is the maximum, this is a graph of profit with respect to time, and this is the time they had the most profit. Or, yeah, there's all kinds of physics examples where we could do this too. Now, I think that this particular section of the book is kind of vocabulary dense, and so let's and there really isn't a good place to start. You kind of have to work your way through the whole thing. Let me show you what I'm talking about here. The first thing that we're talking about, again, is this bulleted list right here at the beginning, is we're going to be finding the maxima and minima of this function. Hey, that word maxima and minima, that's just the plural of maximum or minimum. Like there's 2 maxima here and there's 1 minimum. All right. We're going to be finding these maxima and minima over an interval I. That's the piece of jargon they say, over the interval I. That means like we're just talking about the subdomain over which we're just comparing. Like, for example, maybe we just want to know between, let's just say that's 0 and that's 4. So, like, our interval might be from 0 to 4. Or maybe we mean the entire span of real numbers here, and our interval will be negative infinity to infinity. I guess you usually use curved parentheses when you're talking about infinity, don't you? Alright, so this is just the domain, the span of x values, the interval is the word they're using today. That is what we're taking into account here. And a maximum is just the highest point in that region. But you're going to see that we actually have different, we have absolute maxima and we have local maxima. I want to draw your attention to this word extremum. An extremum is when you're not really caring whether it's the maximum or the minimum. So that could be the max or this could be the min. So like that's an extremum, and that's an extremum. The plural of extremum is extrema. I know, it's hard to keep these guys straight. All right, so when we are talking about this here, we're going to start with the absolute maxima. And let me clear some of this stuff out here. And let's say that we are talking about this as like this interval is from 0 to 4. We're just taking this little piece of the function right here. We're not worrying about what's going on way over here in the negative infinity direction. We're not worrying about over here the positive infinity direction. Then this idea of the absolute maximum of the function is that value f of x right here. I'm going to call that f of c for right now, because then it'll be happening at x equals c. So maybe c is equal to 3, and f of c is the biggest value in that range. In that domain. So in that interval from 0 to 4, apparently at this value of c, of x, we'll call it c, it looks, eyeballing, it looks like it's at about 3 in this case, then f of 3 is the absolute maximum. It is the highest value we see in that interval. And for that matter, in that same interval here, I would say that this is the absolute minimum. So I would say like maybe f of 4 is the absolute minimum. So in other words, there's an absolute minimum at x equals 4. That'd be another way to put that. Notice that this is the minimum, not this. This is going to have another word. There'll be a word local minimum to describe this. But this is the absolute minimum. In that domain, in that interval from 0 to 4, that is the smallest value of f of x. Notice that the word absolute maximum and the term absolute minimum have nothing to do with absolute value. Okay? Absolute maximum means it's farthest this way on the graph. Absolute minimum means it's farthest that way on the graph. All right. Now, we have to be careful with the wording of this because we want to make sure that we're doing it right. So, like with this graph here, the way we would state it, let's just say this one right here. Let's just go ahead and say that this point is 3. We would say that f of x has an absolute maximum at how about x equals 3. And the absolute maximum is whatever f of 3 is. In other words, the y value, or the f value on the graph, that is the maximum, and it occurs at this value of x. Okay, different textbooks use slightly different jargon to describe these things, and we want to make sure we're careful about that. All right, at the bottom of page 1 of the handout here, we actually give you a way of writing the actual definition of absolute maximum and absolute minimum. And I do want to make sure we're clear about that. So here we have this interval from 0 to 4. And what we would say is that f of c, again, we'll find where c is along this x-axis here, is the absolute max if f of c is greater than or equal to f of x for all, I guess I forgot that word, for all x in that interval I, or if you want to say 0 to 4. In other words, there is no, here is our f of c. There it is right here. There is no x along the way where f of x is bigger than this one. That makes it the absolute maximum. In the same way, we could have the absolute minimum if f of c is less than or equal to f of x for all the x's in that range, in that domain rather. So like I decided that this was the absolute minimum here because there is no value of x between 0 and 4 such that f of x is smaller than that. So that makes it the absolute minimum. Alright, now, not every function will have an absolute maximum, not every function will have an absolute minimum, especially if you switch to using a domain that's like negative infinity to infinity. Once you start having these domains that are like all real numbers, these intervals that are like all real numbers, we start having trouble finding absolute maxima and absolute minima. I mean, like if I was using the same function here and I said what is the absolute minimum of this function on the interval from negative infinity to infinity, I'd have to say that there is no minimum. Because there is no value of c I could pick such that f of c is lower than any other value of f of x. I mean, no matter how far out I go on c out this way on the x-axis, I could always go farther and get an even lower value of f of x. So in this case, there is no absolute minimum. This will mostly happen to us when we're using an interval that is negative infinity to infinity. But if we have a limited domain, like 0 to 4, we really should have an absolute maximum and an absolute minimum. There are some ways where we can't have it, but as long as the function is nice, it's continuous, it's differentiable, all that kind of good stuff, we will have an ability to find an absolute maximum and an absolute minimum. And at that point right there in your handout on page 2, I actually cut and paste some figures from your textbook into it. And most of them are pretty self-explanatory. Like if I look at figure B, the second one on there, you have a little graph that looks something like this. And they say on the interval from negative infinity to infinity, we would definitely see that there's some kind of absolute maximum here. We have an absolute max of, it appears to be f of 0, at x equals 0. And we can actually plug in the values. It gives us the equation right there, but we won't do that right now. All right. But what's interesting about this one is they say no absolute minimum. Right? Because this is just asymptotically approaching the x-axis here. No matter how far down the x-axis, if I made c equals 1 million, I'll have a pretty darn small number here. But if I just picked c equals 1,000,001, I'd have an even smaller number on the graph. There is no value of c I could pick where I have the smallest possible value of c. So in this case, there is no absolute minimum. I feel the same way about the fourth one there, figure D. a little bit confusing as to why figure D doesn't have an absolute minimum. If I just sort of sketch roughly what they have right there, it looks something like this. Right? And it sure looks like there's some minimum here. I think that is at x equals 2. But they're going to say on this function there is no absolute minimum. They gave us a domain, I forget, an interval rather. I mean, you might be tempted to think it's at x equals 2, but remember x equals 2 is going to map to this as f of 2 right here on this piecewise function. And I could pick, you know, pretty darn small, but I could say f of 1.999, which is a pretty darn small number here, but that's going to be bigger than f of 1.99999, which is going to be bigger than f of 1.999. No matter what value of c I pick, I could always pick one closer to 2, and that will be even smaller, so there is no smallest value of f of c. And so it's a little hard to see on these piecewise ones, but there won't be this function won't be able to have an absolute minimum necessary. But the trick, of course, here was that that function wasn't differentiable. It wasn't continuous. And that's actually going to be kind of our little loophole here if we go on to problem 3. This is called, I'm sorry, page 3. This is called the extreme value theorem. And the extreme value theorem is going to tell you that as long as you're working with some closed interval, so we're not talking negative infinity to infinity, then if the function is, let's see here, if the function is continuous, then there will be an absolute max and an absolute min. Alright, that's our extreme value theorem. It's way beyond the scope of this class to try to solve that, or to prove that or anything like that. But basically it makes common sense. If we have some kind of interval, let's say we're talking about from here to here, and our function does something, as long as it's continuous through that whole thing, there will be some place that is the biggest value, and there will be some place that is the smallest value. It might even be the endpoints, it isn't in this case, but there will be some place that is the absolute maximum and the absolute minimum in that closed interval from A to B in this case. Alright, once you see a graph here, the extreme value theorem is actually not such a mysterious thing. It's just kind of hard to picture it based on the words of that definition. So far what we've been looking for has been the absolute maximum and the absolute minimum of the function. But lots of functions will have more, you know, I sketched something that looked kind of like this at the beginning of the class. Here's our absolute maximum if we're talking about some, you know, interval like this. But this guy deserves some kind of prize too. I mean, he's kind of a maximum, and in fact he is, called a local maximum. And this guy right here is a local minimum. There are definitely places on this graph that we deserve some kind of honorable mention, and we'll call them a local maximum and a local minimum. Now, I give you the technical definition of local maximum and local minimum there on page 3, and it comes from your textbook too. But I think that's a little bit fussy and hard to understand. It starts talking about you could come up with an interval. Here's a little tiny interval, and in there it is the absolute maximum. Or here's a little tiny interval around this place, and it is the local minimum. But that gets really hard to understand what's going on. Let me tell you what a local maximum is kind of in words. A local maximum means it's downhill this way and it's downhill that way. A local minimum means it's uphill this way and it's uphill that way. Okay? We don't necessarily need to go into this derivation, this complicated definition that they provide there for local max and local minimum. Alright. The local max is, I mean, this is a local max too, but he happens to also be the absolute max. Local maxes may be the absolute max. The absolute max might be a local max. Why wouldn't it be always that an absolute max is the local max? Let's say the function looked like this, and this was our interval. On that interval, this is the absolute max, but it's not a local maximum. This is a local maximum over here. Alright, so other than the fact that we've dropped the word continuous a couple times here, you probably would wonder what the heck this has to do with calculus. And to understand the connection between this and calculus, we have to have one more definition, and that's this word critical point. And that's at the top of page 4 of your handout. A critical point of a function is the values of x where f prime of x is either equal to 0 or f prime of x is undefined. Undefined, of course, normally meaning dividing by 0 and it blows up. Those will be called the critical points of the function. And we'll be finding critical points of functions, but critical points of functions will local maxima and local mins will be there. Will be at critical points. Not necessarily, okay, let me finish this up here. Not at critical points. There might be more critical points than just the local maxima and minima. You guys will see in just a little bit. I mean, for example, a function that does something like this point right here will turn out to be a critical point, but that's not a maximum or a minimum. That's called an inflection point. But those will be the places we'll start looking for our critical points. So like on the bottom of page 4 right there, I have an example. It says f of x is equal to 1/3 x cubed minus 5/2 x squared plus 4x. And it says find the critical points and then use Desmos to determine whether it has a local extremum at each of those critical points. Okay. So since we're trying to find critical points, and critical points are the places where the derivative is either equal to 0 or the derivative is equal, well, it's undefined, I guess the first step we need to do is find the derivative. It's 1/3 times 3x squared minus 5/2 times 2x plus 4. Hey, lots of simplification can happen here. Like that. Alright, critical points will be places where this derivative is equal to 0 or undefined. I don't see any way to get this one to undefined. That's typically going to happen where you have terms that are like something over x, so that when the x gets, the denominator can become equal to 0, the whole thing blows up. There's nothing like that in here. So instead on this one, what we need to do is find the places where this derivative of it is equal to 0. You could do any of the brilliant things that you learned in Algebra 2 here. You could use things like the quadratic formula. Feel free to just, really torture yourself and use completing the square. In this particular case, I'm not afraid of the factoring. I believe it is like this, and that would be fine. And I like the factoring on this particular one because this is a classic example then of where you have two terms multiplied together and they make 0. It's called the zero product rule I just recently learned. So either x minus 4 is 0 or x minus 1 is 0. Means x is equal to 4 or x is equal to 1. These are our critical points. We've answered our first part of the problem there. Then it says, make a graph of this in Desmos and tell me if those places are extrema, local extrema. Alright, so I can't bring up Desmos right now in front of you, but you have the handout in front of you, and you can see the graph that I made, and I'll just sort of sketch it a little bit right now. But if we had a graph of this function here, it looks to me like it does something like this, and then like this, and so on. And one of our places was at x equals 1, and this would be f of 1. And the other place is right here at x equals 4. And this point right here is f of 4. And it looks to me like this one is a local max. And it looks to me like this one, this critical point over here, is a local minimum. Cool! That wasn't so bad. Okay. It wouldn't have had to be when we actually made the graph. If there had been something like an inflection point, that's a critical point, but it wouldn't necessarily be able to, it's not a maximum or a minimum, for example. Again, the function is nice and continuous, so we didn't have to worry about anything terrible the way we do with like piecewise functions and so on. I'm embarrassed on this last problem on page 5, how long it took me to get this one right. I made lots of mistakes with it. Let me get a drink of water here for a second. I made so many mistakes on the one that's labeled another example on page 5. Basically, we're doing the same thing, but for a new function here. F of x is equal to 4x over 1 plus x squared. Well, the problem specifically asks us to find the critical points and then to find use Desmos to find if they are if those are maxima or minima. Let me make sure I actually did put that graph in here for you. What? Yes, I did. Okay. All right. Well, then, since it's about critical points, the first thing I do is find the derivative of this. And it's clearly a quotient rule problem. So we got the derivative of the first term times the second term minus the first term times the derivative of the second term all over the bottom term squared. All right. I would not leave it like that. I would go 4 plus 4x squared minus 8x squared over 1 plus x squared squared. And that's actually, this is where I kept making the mistake. I hadn't noticed that this simplifies to this. Let's just leave the bottom part alone for now. So here's our way to write the derivative. We'll use this one right here. All right. First off, what we need to do is to find the critical points, and the critical points will be the places where the derivative is equal to 0 or it's undefined. Now, your first thought would be like, oh, alarm bells should be going off here. This looks like this might be able to be undefined if that denominator is ever equal to 0. But you can play around with this a little bit and see there's actually no way to get that denominator equal to 0 if x is a real number. You can see that the only way you get the denominator equal to 0 is if this inside part was equal to 0, because then you'd square it and it would still be 0, which means x squared equals -1. Well, good luck with that unless we start allowing imaginary numbers or something like that. So we don't need to worry about the idea that this one can allow some undefined places to be critical points. What about places where the derivative is equal to 0? Well, those would be places where the numerator is equal to 0. And with a little fussing, you'll be able to see that that is x equals plus or minus 1. Okay, so apparently we have two critical points. These are our critical points, which is part of what the problem was asking for. They are places where, in this case, the derivative is equal to 0. Then it says, use Desmos to tell me if those are extrema or not. All right. Well, again, I can't pull up Desmos right here in front of you, but I did put that into the handout, and I'll sort of roughly sketch the diagram that you have at the top of page 6. It looks something like this, where this is x equals -1, and this is equal to x equals 1. All right. Well, clearly, f of -1 is a local minimum, and clearly f of 1 is a local maximum. Now, in this particular case, we can also see they're actually both. This is actually the absolute minimum, and this one actually is the absolute maximum as well. Why does this work? Well, remember the derivative is a way of saying the slope of the function. And basically what you're doing is you're finding places where the slope is equal to 0. Well, the slope is equal to 0 at the place where it flattens up and turns go around the other way. Those will be the maxima and the minima of the function, as long as the function is smooth and continuous and all that kind of good stuff. All right, cool. Those were finding local minima and local maxima. We actually need a new rule if we're going to find the absolute maximum and the absolute minimum. To actually define the absolute maximum, and then we can just switch the definition around for absolute minimum, it's going to be in some interval, in some bounded interval. I'll just write like a, b. So like between x is between a and b. Then the absolute max will be at one of the following. It's either at one of the endpoints or a critical point. Those are the only places the absolute maximum can be. And for that matter, we could just cross this out and say the absolute minimum. The absolute minimum in that fixed range will have to be at either the endpoints or at a critical point along the way. And probably the easiest way to do this is just to show you an example. So down at the bottom of page 6, we start an example that goes all the way to the bottom of page 7. And the function that we're working with here doesn't look so terrible. It's negative x squared plus 3x minus 2. All right? And we're supposed to find the absolute maximum and absolute minimum of that function on the interval from 1 to 3. In other words, x has got to be someplace between 1 and 3 on this function here. We're not going to graph it or anything like that just yet, although you're certainly welcome to peek ahead to page 7 and see what this thing looks like. But, alright, we know that the absolute maximum and the absolute minimum will either be at an endpoint or at a critical point, so I guess we better go find the critical points. Okay, the critical points, remember, we got to find the derivative, which is super easy in this one. And then we say, are there any places where that's undefined? Well, this doesn't have any like divided by x's or anything either. This will never have a divided by 0 in it. We don't have any undefined places of this derivative. But we might have places where this is equal to 0. Let's see here. Negative 2x equals negative 3, x equals 3 halves. That's a critical point. So, now we have our absolute maximum and our absolute minimum have to be at either the endpoints or at the critical point. Well, there won't be so many of these places. Just plug them in. Find f of that first endpoint, which was 1. And if you actually do that, I think I did it on page 7, f of 1 turns out to be 0. Try that critical point, 3 halves, which, by the way, notice 3 halves is in the range from 1 to 3. That's good. Alright, that happens to be equal to 0.25. And the other endpoint, which was at x equals 3, f of 3 is equal to negative 2. These are our 3 candidates for being absolute maximum and our 3 candidates for being absolute minimum. Well, clearly, this one is biggest. It has the biggest value of f of x. So this one is the absolute maximum. And this one is clearly the smallest, so it is the absolute minimum. Which is pretty cool. We didn't even need a graph to find what the biggest value and the smallest value of that graph on some interval was, although the graph has its charm. If you actually make that graph, it looks something like this, where this is at 1, 0, this spot right here is at 3 halves, 1 quarter, and this spot right here is at 3, negative 2. And clearly this is the absolute minimum, and clearly this one is the absolute maximum on this domain, on this interval. This is hugely powerful because finding the maxima and minima of functions is a big part of optimization. It's a big part of how we pick the best of anything or the most efficient or whatever. A lot of the applications of calculus come from this stuff. Alright, so I'm going to be putting a homework set up for you on Google Classroom. I'll post section 4.3 of the book as well, and I will also give you guys an exit ticket. I hope that gets you everything that you need. I hope that you're doing well, and please let me know if you have any questions or anything. I like hearing from people. We're all a little bit stir-crazy being locked up in the houses, so please let me know if you have any questions.